Hi guys, this is Mrs. Foy, and this is a screencast on periodic trends and what we call periodic law. So what you should have at the ready is you should have a periodic table to look at because that's really important. And you also should have your note sheet. So you might have an electronic copy of this, so it's a blank periodic table, and then you have your note sheet, either virtual or a hard copy, because that's what I'm going to have you take notes on. And of course, if you're in my class, this is going to be used for a quiz that's coming up. So you want to take good notes, all right? Because you're going to be able to use those on the quiz. So we want to learn, we've already done a lab, or if you haven't already, you will be soon, looking at if we can see any patterns or trends about how reactive certain elements are. And of course, as a chemistry person, you want to know about chemical reactions because that's what chemistry is. And in order to understand that, you need to understand atoms and their electrons, because chemical reactions occur when electrons interact. And if you understand that, you can use the periodic table and do some very powerful predicting. And that's what makes chemistry so fun and so powerful. So here we go. On your periodic table, your blank periodic table, it would be really great if you had some colored pencils or some crayons or a highlighter, anything like that. You're going to be marking and outlining some of these columns or families, all right? So that's what we're going to work on for the next couple of slides. You may have to pause this lecture to catch up, but that's what you should be working on right now, all right? So the group one, or in the old periodic table, they were called Roman numeral 1A, and the shorter columns that you see right here were the B columns. Now we just number them 1 through 18, so it's a lot nicer. But we call these guys the alkali metals. So go ahead and highlight those on your blank periodic table. As you know, these guys like to form a +1 charge. They like to lose an electron when they can to have a more stable electron configuration. They are highly reactive, as you saw in the demo that I did in class with the alkali metals and water. And they are very good conductors of heat and electricity. So we're going to be doing some more labs that let you explore that. The next column is the alkaline earth metals, and they are the second most reactive group. The alkali metals are the most reactive. This group, group 2, or this family called the alkaline earth metals, are the second most reactive group, and they like to form a +2 ion when they have a chance. Okay, so obviously the atoms are neutral. They have the same number of protons as electrons, but when these guys have a chance, they like to lose 2 electrons to be more stable, to have a noble gas configuration. The transition metals are the next group. And so these we know are the Ds and the F block. And they have a lot of d electrons. Remember, the d electrons, you can have 10 electrons in those d orbitals. And down here in the F block, you can have 14. Now, those are not the valence electrons. There's only 2 valence electrons, because remember, with electron configuration, the principal energy quantum number, or the rho number, always drops down 1 when you get to the Ds, and it drops down 2 when you get to the Fs. And so the transition metals and these metals down here are always going to have 2 valence electrons, but because the D energy orbitals and the F energy orbitals for the electrons are so close together, sometimes the electrons jump back and forth. And so because of that, we say they have variable charges. They're always going to be positive, but they're going to have variable charges. And that's why we use Roman numerals for this group, right? To show the charge, because it can be variable. But they all have 2 valence electrons, and a lot of times they make a +2 ion. And then we have group 17, or group 7A in the old way of numbering columns, the halogens. And the halogens have 7 valence electrons. So you can count over 1, 2, 3, 4, 5, 6, 7. 8 is this next group we're getting to. But the halogens like to gain electrons. And so they like to become a -1 ion. And they are more stable when they have that configuration, because they are going to be very similar to the electron configuration of a noble gas. And that's our next group, are the noble gases, group 18 or group 8A. These are also called the inert gases. Inert means they don't react. And we're going to learn that that's because they already have the full set of valence electrons. Valence electrons, remember, they are electrons in the outer energy orbitals, and they already have 8. And 8 is the perfect number. It's the most stable for the atom, according to the quantum mechanical theory of the atom. And these are very highly unreactive. It used to be thought that they didn't react at all. But we know now, under special circumstances, the noble gases can react, but for the most part, they do not. So the first row of the F block we call the lanthanide series. We have a special name for them. Sometimes we call the inner transition metals, or the rare earth metals. Only one of them is radioactive, and most of them are found naturally on the Earth. The actinide series are the 5F. They are all, again, inner transition metals, and all of them are radioactive, and most of them are not found naturally on Earth, with the exception of a few, notably uranium. So we know about this great staircase that divides the periodic table between the metals and the nonmetals. And your periodic table already has that drawn on there. So, of course, most of the elements in the periodic table are metals. The great majority are metals. We know that metals like to lose electrons. All right, so you're going to keep that in mind. And when we do nomenclature, we always list the metals first and then the nonmetals. The line over to this right, this great staircase line, also has our nonmetals, which include the halogens and the noble gases. But some of the elements that touch the great staircase are what we call metalloids. And metalloids are like silicon. So if you're in my class, you saw silicon yesterday. Silicon looks like a metal. It's kind of shiny and silver, but it feels more like a rock. It's not ductile, it's not bendy. And so it has kind of metal and non-metal characteristics. But these 6 elements are considered to be metalloids. So let's do a brief history of the periodic table. And at this point, you should be on the very back of your packet where it says extra notes intro. All right, so this is where you're going to be taking some notes. So in the late 1800s, early chemists had already discovered a lot of elements. And they began realizing that these elements needed to put them in some kind of a table so that they could be well organized and we could learn from them. And there was a guy named Mendeleev, a Russian named Mendeleev, who arranged the periodic table by atomic mass. So he put the lightest elements first, and then he started filling in with heavier and heavier and heavier elements. And he noticed that there was a repeating pattern of how these elements acted. So for example, he could see, and of course, not all the elements were discovered then, but he began to see that every 8 elements, that there was a repeating pattern about the way these atoms reacted. And so you can see that some of these he put in the in what we call now the alkali metals. Now, copper is not there anymore, and neither is silver, but hey, for 1869, he did pretty well, right? But there was a problem. And so there was somebody else that came to the rescue. But the first thing I want to say is I want to tout his success, because one of the things that he did was he predicted that there would be elements that were yet to be discovered, and he could predict their atomic mass. And lo and behold, he was right. And that really won him a lot of followers. And so some of these elements that weren't discovered yet, when they were discovered, they had the atomic mass that Mendeleev said and that he predicted by his periodic table. So this was the birth of the first periodic table. Then there was another guy named Henry Moseley, who in 1913 corrected the problem of having the atomic masses. And I should say, I need to point out that there is a couple of problems here about where the atomic mass did not go in order. And so what Moseley suggested is arranging the elements in ascending order of atomic number, right? That's the number of protons. And once he did that, the modern periodic table really was born. And so we know today that for the most part, the atomic masses also are in order, but there's a couple of places where they are not. And so that's really important to note. But the putting the elements in order of their atomic number is what we do now. And so we see a clear pattern of every 8 elements, especially those that are in the major tall columns. We see something called periodic law. And what periodic law is the repetition of the chemical and physical properties of those elements, like the alkali metals, like the fact that they react very strongly with water, and like the fact that they all like to become a +1 ion, things like that. So this goes back to what we call the octet rule. And octet means 8. And so all atoms want to achieve 8 electrons in their outer shells. That's what atoms live to do. They want to get to 8. And they're going to do this if they don't have 8. Remember, the only atoms that have 8 valence electrons, so these are the electrons in the outer shell that are the highest energy, they do it by either losing electrons or gaining electrons, or sometimes they will share electrons to get 8, depending on their characteristic. So at this point, on the first page of your notes, you can write down, you can pause the video if you need to, and write the octet rule. So just a reminder about electron configurations, that we can see the S block here and the P block here and the D block here and the F block here. We know that the rows are the major quantum numbers, principal energy numbers, or the row number. We can see that helium really goes right here. And we can see that the width of the block is the number of electrons that are in that. So S's can only hold 2, D's can hold 10, and P's can hold 6. And we see how we get to 8, right? So for example, in the second energy level, we have 2 in the S block, and then we have P's, right? We have 6 electrons that can be in the P energy level, and that's how we get to 8 for our noble gases. And so this diagram shows just that, right? This is showing a Lewis dot diagram. And a Lewis dot diagram is basically a cartoon of a depiction of the valence electrons. And so we kind of put like an imaginary box around these guys, and we put 2 dots per side, and we spread them out so that they're not clumped together unless they have to be. And we can see helium really is going to go here, right? Because it's got 2, but we put it over here because there's only 2 electrons in the first energy level. So technically it's a noble gas, even though it's an exception to the octet rule. And so we see this pattern, right? We have 8, 7, 6, 5, 4, 3, 2, and 1 valence electrons. So now I'm going to give you a quick definition of the vocabulary terms we're going to work on. And these are the concepts that show a periodic trend. In other words, they show a pattern. All right. And 3 of these are going to be especially important to us. All right. So I'm going to give you a quick definition, and then we're going to go on and explain more. So atomic size is the atomic radius. It's the same thing. So it is literally a measurement of the size of the atom from the center of the nucleus out to the outer electron cloud where those outer electrons should be. All right. And that measurement is a measurement of the atomic size, or what we call the atomic radius. The next periodic trend, and we see a trend of that, is we're going to see there's a pattern to what size these guys are. Ionization energy is the energy needed to remove an electron. So to pull an electron off. If you have to pull really hard to get an electron off, then that's a high ionization energy. If it's easy to pull an electron off, that's low ionization energy. And that's going to become important as well. Electron affinity, affinity means you like something. So electron affinity is actually the pull an atom has on its own electrons. And that's going to be okay important for us. I'll say it again. Electron affinity is the pull an atom has on its own electrons. That's minorly important, but what we're going to focus on is the next concept, electronegativity. And electronegativity means the pull one atom has on another atom's outer electrons. So I'll say that again. Electronegativity is the pull one atom has on another atom's outer electrons. And that's very important in chemistry, and we're going to see a pattern for that. And then finally, we're going to talk about ionic size, and that is the size of an ion, either a cation or an anion. All right, so this is just a review of what we've already learned doing our POGL on Coulombic attraction. But just remember that the higher the N, the higher the principal energy number, or rho, the larger the orbital is, right? Electrons are added like the rings of an onion, further and further away from the nucleus, the higher energy they go. And so we're going to see a pattern that the Coulombic attraction, which is the pull, the force from the positive protons in the nucleus to the outer electrons, which are negative, right? So we know there's an attraction there. And that is going to change depending on if you're going down a column or across a row. This is just review, okay? So if you go down a column, like here in the Alkali Metals, if you go down a column, we see that the Coulombic attraction gets weaker because the distance from the nucleus to the outer electrons is further away. So as you go from lithium's row to sodium's row to potassium's row, the electrons are added further and further away from the nucleus. And so the pull, the Coulombic attraction, gets weaker as you go down a column. As you go across a row, the attraction gets greater. And the reason why is that as you go across the row, so if you look at the third energy level, or the third row, third period, sodium, aluminum, and chlorine, all those electrons are getting added basically the same distance from the nucleus. So sodium has 11 protons and 11 electrons, aluminum has 13 protons and 13 electrons, and chlorine has 17 protons and 17 electrons. But do you see that when you add electrons, you're not adding them further and further away? It's in the same energy level where you're adding those valence electrons. And so as you go across a row, the distance is the same, but the number of protons in the nucleus is greater. And so there is a greater Coulombic attraction as you go across a row because there is a greater pull from the nucleus because you're adding more protons and the electrons are the same distance from the nucleus. So now that I've reviewed Coulombic attraction, we're ready to pull all this together and actually look at the pattern. So now you're going to be taking notes right here where it says atomic size or atomic radius. So we're going to be looking at the pattern of the atomic size. So when you graphed these, you saw that as you go across a row, so now your eye should be looking at your periodic table as you follow along with me. As you go from hydrogen to helium, the atoms get smaller. As you go in the second row from lithium to neon, they get smaller. Same pattern. From sodium to argon, they get smaller, smaller, smaller as you are going from left to right across the row. And it's the same pattern for every single energy level. And so that is our periodic trend. The trend is that as you go down a column, it gets smaller. And as you go down a column, it gets, the atoms get greater size. And as you go across, they get smaller. But I'm going to tell you a little story about the two Fs. So we have fluorine and francium. And those two atoms, and again, just ignore the noble gases because we really don't include those in our periodic trends because remember, they're not reacting. Those two atoms, the two Fs, are the most opposite of any two atoms you can probably think of, all right? Francium is a very big fat atom. I mean, it's got 87 electrons. They're way out there. It's a big, obese atom. Very weak Coulombic attraction, right? We know as you go down a column, the Coulombic attraction is going to get weaker. And we know going this way, the Coulombic attraction is going to be greater. So now let's look at the opposite F, which is fluorine. Fluorine is a very small, tightly held atom. In other words, it's really holding on to those outer electrons. There's a very, very strong Coulombic attraction. So I'm trying to make this so that you do not have to memorize a lot of things that you'll get nervous and you will forget on a quiz or a test. If you can remember the tail of the two Fs, fluorine and francium, this will help you see the trend. Francium, big, fat, obese atom that can barely hold on to its valence electrons. Fluorine, small, tightly held, very strong Coulombic attraction up in this corner of the periodic table. So here is our trend. We always draw an arrow towards increasing. So as you go down any column, you are going to increase the size of your atom because the Coulombic attraction gets weaker. And the protons in the center can't hold on to the electrons as they get further and further away in the atom. That's really important you understand that. And fluorine we talked about, see how this is pointing to francium, right? The biggest atom with the weakest Coulombic attraction. Over here we have fluorine, and fluorine is very small, but it's also at a very high Coulombic attraction. And so as you go to the left, those atoms get bigger and bigger and bigger because the Coulombic attraction gets weaker. And so the periodic trend for atomic radius is going to be increasing going down and increasing going to the left. So at this point, you're going to want to pause the video and answer the question where it says, summarize in your own words, explaining why the trend is this way and using the word Coulombic attraction. So you should draw on your atomic size diagram those arrows that show increasing. So that's what you need to do at this point. You can pause the video and do that. All right, our next periodic trend is going to be ionization energy. All right, so now you're on this page that says ionization energy. And remember that it is easy to remove an electron that is not held very tightly by its nucleus. Remember francium? Remember big fat francium down here? Big fat francium cannot hold on to its valence electrons. They're way out there and it has a weak Coulombic attraction. So taking an electron, removing an electron away from francium is like taking candy from a baby. Super easy. Very low, what we call ionization energy. And fluorine up in this corner, right? The other F, fluorine is a small atom that has a high Coulombic attraction, and trying to remove an electron from that fluorine is very difficult, right? Because it's got a strong Coulombic attraction. So why is everybody trying to either remove electrons or whatever? They're trying to get to 8. That is the name of the game. Every atom wants to get to 8 valence electrons. So ionization energy is the energy needed to pull off an electron. And technically, this is the first ionization energy, which just means the first electron. It actually changes a little bit for the second and third electron that is removed. So if you have francium, think about it. If you have francium, is that going to be a low ionization energy or a high ionization energy? Right. It's going to be a low ionization energy. It takes a little bit of energy to pull off that electron from francium because it has a very weak Coulombic attraction because the valence electrons are way the heck out there. Think about fluorine up in this corner. Fluorine has a very strong ionization energy. It has a high ionization energy because it is holding on to its electrons really tightly, and it's hard to remove one. So you saw this when you did your graphing. Let's look. And again, look at your periodic table to see the pattern. As you go from hydrogen to helium, the ionization energy gets stronger. As you go from lithium to neon, ionization gets stronger. Same thing in the third row, from sodium to argon, ionization gets stronger. So we see a repeating pattern as you go across a row of it getting stronger and stronger and stronger. But look what happens as you go down a column. You can see that the ionization energy is going to be lower. So here is our trend. Again, think about the 2 Fs. Who has, again, ignore these noble gases because that's kind of the easiest thing to do because they really don't react very much. Who has the highest ionization energy? It's fluorine. And so think about everybody who has the lowest, francium. So the ionization energy is going to increase going up a column, and it's going to increase going across a row because the Coulombic attraction is going to increase going across a row, and the Coulombic attraction is going to increase going up a column. So it is going to be the easiest, the lowest ionization energy is our francium, and the highest ionization energy is our fluorine. So I hope that will remind you how to draw the ionization energy arrows without trying to memorize them, okay? But they are actually, the ionization energy trends, periodic trends are opposite of the atomic radius. So at this point, you should have drawn those on your table, and take just a minute to summarize why the trend is increasing as you're going to the right and increasing as you're going up a column. All right. And if you're confused, you might want to pause and replay that part of the video. So electron affinity and electronegativity. Remember, electron affinity is the pull I have for my own electrons, but electronegativity is the pull I have on some other dude's electrons. And as it turns out, it's the electronegativity is the most important for first year chemistry students to understand, because that has to do with bonding. Okay, so remember the octet rule. Every atom wants to have 8. They're going to beg, borrow, steal, whatever they have to do to get 8. And if I have a very strong pull on somebody else's electrons, that's really going to help me have 8. But as it turns out, the electrons that have a low electronegativity, sometimes they're like, go ahead and take my electrons, because that way I can lose electrons and then I can get to 8 valence electrons by losing. Remember, who has the perfect set of 8? It's the noble gases. So everybody wants to get to electron, the electron configuration of a noble gas. They're not going to become a noble gas because the protons are different, but they're going to have their electron be like a noble gas electron configuration. So electronegativity, now we're going to look at this page. All right. So let's see if we can figure out why this is happening. Again, let's look at our F's. Forget about the noble gases because they already have 8. They're already perfect. We don't care about them. Let's talk about fluorine. Fluorine, what do we know about fluorine? Fluorine is small. Fluorine has a tight Coulombic attraction. It has a very high ionization energy. And fluorine is the most electronegative atom on the periodic table. If you get anywhere near fluorine, fluorine is going to pull and pull on your electrons with a very strong electronegativity. And in most cases, it's going to be strong enough to rip an electron off of you. So you better hold on to your electrons when you're around fluorine. Our other F is francium. Let's think about francium. Francium is a big, fat atom that has a very weak Coulombic attraction, right? Because the pull from the protons way out here to electrons is very, very weak. My gosh, francium can barely hold on to its own electrons. It is not going to be pulling off yours, okay? And so I can see the trend here. The trend is going to be increasing as I go up and increasing as I go to the right. And that's an important trend. Go ahead and draw that on your electronegativity table. And notice that it actually has numbers there. And that's going to become very important when we learn about what kind of bonds atoms make. So you see that fluorine has an electronegativity of 4. And we see that francium has an electronegativity of 0.7. Okay. So again, this is going to set up bonding. All right. So let's say the two F's get together. Let's say fluorine and francium get together. Well, those are two opposites, right? So francium, big fat francium, can barely hold on to its own electrons. Fluorine, super small, pulling on its own electrons, really has a strong electronegativity, is going to start pulling on yours. What do both of them want? They both want the same thing. They want 8 valence electrons, but they're going to get it in 2 different ways. What's fluorine going to do? Well, fluorine is going to rip off francium's electrons, because if it does, then it can get to the noble gas electron configuration of neon, as we saw. So it becomes fluoride, which is -1. And francium, what happens to francium? Francium gets its electron pulled off, but it's like, fine. That's the best thing that could ever happen to me, because now francium is going to become a +1 ion, which has the electron configuration of radon, right? And so both atoms get what they want, which is noble gas configuration, 8 valence electrons, and they're actually going to form what we're going to learn is an ionic bond. The +1 of the francium and the -1 of the fluoride are going to bond. But that's getting a little ahead of ourselves. So now what I'd like you to do is to just take a minute to explain and summarize why the electronegativity goes up as you go up a column and why it increases as you go across a row, and explain that in terms of the Coulombic attraction, remembering the 2 F's to try to help keep it straight in your mind. So let's review very quickly about these 3 periodic trends that are going to be the most important for our class. The atomic radius trend, right? We know which ones are the biggest and which ones are the smallest, right? They're going to be bigger going down because francium's the biggest, right? And bigger going across. Atomic ionization energy, the first ionization energy, is how much energy it takes to pull off an electron. Well, that is going to be the highest ionization energy for fluorine, right? Because that's the smallest atom. Again, ignoring the noble gases. So it's going to increase going this way, and it's going to increase going up. Atomic electronegativity is the pull one atom has on another atom's electrons. And so that, again, the most electronegative atom is fluorine. And so we're going to increase going across this way, and we're going to increase going up. All of these can be explained, of course, by understanding the octet rule and the electron configurations, knowing that everybody wants to be isoelectronic to a noble gas. And remember that chemical reactions occur when electrons interact. And so that's going to set up bonding, which is what we're going to learn about next, where atoms either steal electrons, like my story with the fluorine and the francium, or they're going to end up sharing electrons if their electronegativities don't allow one to be a clear winner. So I did a separate screencast about ionic radius. And if you feel that you understand that and you don't want to have to listen to me explain it again, then you can go ahead and stop this lecture right now. If not, you might want to hang on so that you can make a summary of the ionic radius here, okay? So what we need to remember is very simple, is that positive ions, cations, are going to get smaller when they lose an electron. And negative ions or anions are going to get larger. So let's see if we can figure this out without having to memorize, okay? Look at your periodic table. Sodium has an atomic number of 11. That means the atom has 11 protons and 11 electrons, and this is the radius. It's 186 picometers, all right? Which is very small. When sodium loses 1 electron, which is what it wants to do to be isoelectronic to neon, it is now going to have 11 protons still because it's still sodium, but now it only has 10 electrons. So I have 10 protons pulling on 11 electrons. That's easy to see what's going to win. And that cation is going to go whoop. It's going to get a lot smaller because I have 11 positive things pulling on only 10 negative things. So cations get smaller. Anions are going to get larger. So let's look at the chlorine atom. The chlorine atom has 17 protons and 17 electrons, right? But when chlorine gains an electron, which it's very easy to do because look, chlorine is right under fluorine. And I know that fluorine is very electronegative. So what do you think chlorine's going to be? Pretty electronegative too, right? It's up there in this electronegative corner where the F gang hangs out, all right? And so chlorine is going to very easily be able to pull an electron off somebody else and become chloride, which is a anion. And what happens now is here I had 17 positive things and 17 negative things. In chloride, I have 17 positive things pulling on 18 negative things. And so the electrons are going to expand a little bit and to try to get away from each other, and also because there's a little bit less Coulombic attraction. And so it's going to get a little bigger. All right. So anions are going to be larger than the atom that they were, and cations are going to be smaller. All right. And I hope that helps, and hope you took good notes, because you're going to be able to use these on a quiz more than likely. And I will see you in class.